Welcome. Welcome to Unit 2. You survived Unit 1. You're probably super excited now to learn all there is to know about general chemistry, right? General chemistry 2, I mean. So, hopefully you are. But in Unit 2, we're going to switch to talking almost exclusively about chemical reactions. So we really haven't done any of that yet. We've talked about solutions and concentration and that kind of stuff, and we're going to carry that through. But in this unit, we're really going to get into, we have starting materials on one side of the reaction, we have products on the other side of the reaction. What happens next? Do we move from one to the other? Do we go backwards? How fast does that go? All that good stuff. So we're going to talk about rates. Rates of reaction is what we're going to talk about this week. And then next week, we're going to get into equilibrium, which is basically how far does the reaction go and when does it stop. So that's what we're focusing on. Um, yeah, I guess we'll get to it. You'll see there's a fair number of worksheets and practice kind of exercises and such for you here. There will be another homework. There will be a quiz on Friday of week 4 of this. So you'll see all of that on D2L. So watch for that. Okay, so we're going to start with defining reaction rates. And so reaction rates are basically, of course, the speed of the reaction. How quickly does the reaction get to where it's going? And we'll talk about where it's going in a minute, but how quickly do our products of our reaction appear? Now, this is measured by concentration, right? So, of course, when you measure a reaction, we're looking at how much of something is in there. Almost always, we run our reactions as solutions, right? So, you're going to dissolve your products, whether they're solids or liquids, or sometimes even gases. You're going to dissolve them in liquid, and you're going to have a solution that's stirring on your hot plate or whatever. And you're going to add your starting materials to that. You're going to let them dissolve and then react, and then you're going to kind of keep an eye on how much of the product is present at each time as we go through this, right? And so how we're going to always express our rates of reaction is going to be in things like molarity per second, right? So the change in molarity per unit time, right? So if our reaction starts at 0 molar, we have no product in it, right? So 0 molar concentration of product. And then after whatever 60 seconds, we have, I don't know, let's say 0.1 molar of the product. Then we're changing at zero point 0.1 molar per 60 seconds, right? So you can divide that out and figure out what that number is and such. We can also go the other way, right? If we know how much of our reactants we've added to begin with. So instead of looking at the products, if we say, well, our starting solution has a concentration of 2 molar in whatever our starting reactant is. After 60 seconds, we measure it again, and now it's at 1.8 molar, right? And so we've lost 0.2 molar concentration of that starting material. And presumably, it's been converted to product, although that's not always the case. If you get a reaction that doesn't work great, you sometimes get things that don't go from starting material to product, right? They go off and do other things. But that's not what we're talking about. Starting material, we assume it goes to product, so the loss of 0.2 molar of that starting material is also a measure of the reaction rate. 0.2 molar is lost per 60 seconds, and so we can look at that. So there's two ways that we can look at this. Ideally, in an ideal situation, which is mostly what we're going to be talking about, those two rates will be the same, right? The product will appear at more or less the same rate that the starting materials disappear. Now, we have to assume that there's, that's if it's a one starting material molecule creates one product molecule, right? So sometimes you'll have stoichiometry that will change things. We're going to talk about that as well, and you'll get a chance to kind of do the cases where they don't exactly line up perfectly. Right? So first of all, rates are always positive. So we just kind of assume that, even though when we talk about the disappearance of starting material, we just assume that when we're talking about this, we talk about the rate as being a positive number. So rate will always be positive. It's never negative, which is good. But the problem is they're not constant. Rates will change throughout the reaction. So as we get less and less of that starting material in our reaction, those molecules become harder to find. We have a less concentrated solution, right? So if we start at 2 molar, those molecules are going to run into each other pretty commonly. It's going to happen a lot because there's a lot of those molecules in the reaction, right? But as we move down, let's say that we run this reaction for a while, right? Initially, starting materials running into each other, they're reacting, we're creating products, everything's good. After a while, there starts to be less and less of that starting material, and the reaction rate starts to slow down, right? So less starting material in our reaction, a lower concentration of starting material in our reaction ends up resulting in a lower rate. Right? So rates change throughout a reaction, which is not great news for simple calculations, but fortunately, can deal with this, right? We're going to use some math to kind of figure out how, if the rate isn't constant, what are the things that determine how it changes, etc. And it won't surprise you to learn that it's concentration, right? Concentration is going to be the answer to this. All right, so I want to do an example of what this looks like, and I'll show you a graph of the rate, and we'll do all of that. So stick with me. Okay, reaction rates. So let's take a reaction, and once again, I'm going to choose to use an organic reaction because that's all I know. So let's take C4H9Cl and add it to H2O. Right, and then so these are our starting materials here, starting materials. And these are our products. Okay, so the products are going to be C4H9OH and HCl. So you'll notice that we've just done a substitution here. We've substituted, the chlorine atom has been substituted by the OH, and the OH on H2O has been substituted by the chlorine atom. So we just switched their places. So this reaction is a standard chemical reaction, right? And what we can do is we can look at, if we look at, so follow the concentration of C4H9Cl, and we represent that by these square brackets. So if you see a square bracket around some chemical compound, what that means is this is the concentration of C4H9Cl. And we can follow the concentration of that, like we can look at how much of this is present. We can also look at the concentration of the products, right? We can follow the concentration of HCl or a product. Right? So we can also look at the concentration of HCl. Right? And both of these should work because the stoichiometry in this case is 1 to 1 to 1 to 1. Everything has a stoichiometric number of 1. This equation is balanced. And so we know that if HCl is appearing, that an equal amount of HCl is appearing as the C4H9Cl is disappearing. Right? So we can do this, and then we can kind of graph what those concentrations look like. And so I've already done that, and I have a little graph here, right? So here's the concentration of our starting material. At the beginning, we started at 0.1 molar, and then as time goes on, that concentration decreases, right? Which makes sense because, of course, it's reacting, and so as the reaction proceeds toward the HCl and the C4H9OH, this concentration drops. And of course, you'll notice that it's not dropping in a nice linear fashion. This is not a straight line. Instead, you get this kind of curved line where the reaction kind of slows down as we get closer and closer to a concentration of 0. Which is good. So what is the rate of this? If we wanted to know the rate at, let's say, so what is the rate? What is the rate at some time? Right? So if we know that the rate is changing, we can't just say, what's the rate of this reaction? That doesn't really make any sense because the rate of the reaction is going to be different depending on how much of our starting material is left. And so what we do is we make a tangent line. Draw a tangent line. So I'm going to draw a tangent line down here. It doesn't really matter where. Right? So a line that just barely, oh, that's a terrible tangent line. I'm going to try to draw a different tangent line. Give me 1 minute here. Man, my drawing tools are letting me down. This is much easier on a whiteboard. There we go. Oh gosh. All right, so pretend that that's a tangent line, right? And it strikes this, the curve of the rate at this point. Right, so that's at a, well, let's say, what's that, 575 seconds? Right. Draw a tangent line at 575 seconds. The slope of that tangent line, now hopefully you guys aren't trying to do this on a writing tablet, but the slope of the tangent line is equal to the rate at 575 seconds, right? So we can look at the rise over the run of this, right? So if we look at this, this goes from, here's our rise, right? The y-axis changes by, we got from here to about, this is 0.02 up to about 0.043, 0.043 minus 0.02 0.023, so that's our rise, and then we divide that by the run, which is the x value, right? And so we go from 400 seconds out to, where does this hit? Let's say right here, so that's what, 700 seconds? 700 seconds minus 400 seconds, 300 seconds. So 0.023 molar, this is the change in molarity over the change in time, right? So this is molarity per second. 0.023 divided by 300 is some number. I don't know what that is because I'm doing this on the fly. Oh man, now my calculator's not going to start. So let's pretend that there's a number here, 0.023 divided by 300. And I get 7.6 times 10 to the negative fifth. Molarity per second, right, as the rate at that moment. Okay. So now imagine if you picked a tangent line up here, right, that tangent line is going to be steeper. You're going to have a much bigger number for your rate at time, whatever, 100 seconds as opposed to 575. Okay. Okay, so this is a way that we can kind of find the rate at any second. And so what we would do is we would have a table. So on one of the worksheets, you actually get the table of data, right? We'd have a table of data that says, all right, in one row, we're going to have the concentration of C4H9Cl. In the other one, we're going to have a time, right? So time in seconds. And so in the lab, you'd be sitting there and you'd have your stopwatch out and you'd have somebody else watching whatever measurement you're using. So it could be spectroscopy or it could be doing a titration or something that says this is what the concentration is. And then you run your at your stopwatch and you say, okay, at 300 seconds we have this concentration, at 350 seconds we have this concentration, et cetera, right? You just collect all those data points, you get a nice table, you graph that table of data, and you get a curve. Well, okay, so I can't do this right? I'm trying to do this mirrored. So yeah, you get a curve that then looks like the one that I showed. And you can find the tangent lines and find the rate and see how the rate changes as you go on. Now, that's an annoying way to do this. Experimentally, we can find we can collect all this data, we can graph it, we can find the tangent line, we can calculate the slope of the tangent line at each point on the graph, right? We can do all of that, but that takes a lot of time and a lot of work. We need a simpler way to talk about the rates of reaction. And that's going to be the next video where we talk about instantaneous rates. And basically we just kind of say, well, we'll look at what it starts at, and then we'll kind of just go from there. We'll compare everything from time 0, and that way we'll have the same value across all kinds of different reactions. So that's the next video. I've spoiled it already, but you should still watch it because there's good stuff in there. We'll actually get to do some math and such. So I'll see you there. Thanks.